Standard STEM education relies heavily on Eurocentric frameworks, teaching abstract principles that often feel disconnected from a student's immediate physical environment. Within these frameworks, local cultural practices are frequently categorized as folklore or anecdotal traditions, kept separate from empirical scientific study. The Ethno-STEM framework addresses this by translating Indigenous knowledge systems directly into formal scientific curricula. Research published in 2025 by Listiani and colleagues provides a definitive operational framework for deploying this method in modern classrooms. By utilizing this framework, educators contextualize scientific rigor, using a region's cultural heritage as a primary vehicle for teaching complex hard sciences. The production of Jamu, a traditional Indonesian herbal medicine, serves as a practical application of this model, specifically focusing on two beverages, Beras Kencur and Kunir Asem. Traditionally, preparing these drinks involve gathering raw botanicals, boiling them over an open flame, and manually filtering the liquid. Through the Ethno-STEM lens, these brewing practices are analyzed as specific biochemical and engineering sequences. This isometric model illustrates the curriculum's four-pillar framework, which decomposes the production process into ethno-science, ethnotechnology, ethno-engineering, and ethno-mathematics. The objective is to map ancestral claims of healing to validated, quantifiable pharmacopoeias that students can test and verify themselves. We start with the ethno-science layer, which applies modern analytical chemistry to validate ancestral medicinal claims. For the Kunir Asem beverage, students study the specific phytochemistry of its two main ingredients, curcuma domestica, or turmeric, and tamarindus indica. Their laboratory objective is to extract curcumin from the turmeric to evaluate its anti-inflammatory and anti-diabetic properties. To measure these effects, students execute UV spectrophotometry and simple chromatography, analyzing the exact concentrations of the extracted compounds. The curriculum then shifts to the second beverage, Beras Kencur, formulated from roasted rice and aromatic ginger. Biochemical testing here requires mapping how the roasted rice provides the liquid's necessary viscosity and how the ginger releases essential oils that impart an active thermal sensation. These laboratory results provide empirical evidence that traditional community claims of healing are grounded in verifiable chemical realities. The ethnotechnology layer bridges historical preparation methods with advanced food processing technology. Students compare the mechanical efficiency of traditional hand grinding against modern electric extraction. They measure the differing extraction rates of bioactive compounds to determine the efficiency gained when upgrading the tools. Next, they analyze the heating process, starting with the traditional method of boiling the herbal mixture over open heat. They translate this open boiling into the strict thermodynamics of modern pasteurization, learning the temperatures required to kill pathogens without denaturing delicate plant nutrients. The module advances into preservation technology, exploring UV-protected, vacuum-sealed packaging designed to prevent compound oxidation and extend the product's shelf life. Preserving cultural heritage for a modern population requires adapting traditional methods with contemporary food technology to ensure medicinal efficacy and public safety. Ethno-engineering tackles the mechanics of scaling production from small domestic kitchens to hygienic industrial operations. This process flow diagram outlines the systems engineering challenge, designing an optimized, continuous pipeline for boiling, filtering, and cooling the herbal liquids. Within this pipeline, students implement modern food safety protocols to prevent microbial contamination at every transfer point. To solve specific production bottlenecks, the curriculum requires students to design and build their own physical apparatuses. One major project is the construction of a solar-powered dehydration tray, calibrated for processing turmeric rhizomes. This tray dries raw materials efficiently and sustainably, providing a method to prepare ingredients for long-term storage. By applying mechanical design, students learn how to align historical domestic practices with modern commercial viability. The final layer is ethnomathematics, which utilizes quantitative data to ensure product consistency, operational scalability, and economic viability. First, students apply precision measurement, calculating exact turmeric to tamarind ratios to ensure medicinal efficacy in every batch. As shown in these calculations, those ingredient ratios link directly to quantitative chemistry, utilizing mass volume metrics to determine precise antioxidant and sugar levels. With the product standardized, the curriculum introduces an entrepreneurial economics module. The math transitions from chemistry into business logic. Students calculate the raw production costs and operational expenses against potential retail pricing. By calculating the required profit margins, they connect mathematical literacy directly to real-world commercial applications. This framework applies mathematics as a functional tool for localized economic development. The Listioni project demonstrates that traditional indigenous knowledge and modern scientific inquiry are mutually reinforcing. This unified ethno-STEM model fulfills the demands of modern educational reforms, aligning with initiatives like Indonesia's Merdeka curriculum. It develops 21st-century skills while cultivating a global diversity character, a respect for local wisdom mapped to international scientific standards. Students take an active role as engineers of their own cultural heritage, applying rigorous technical standards to traditional practices. Culturally responsive pedagogy demonstrates that integrating local knowledge provides a pathway for students to engage with hard science while maintaining